We're just about there. Welcome back, folks. And we made it. Welcome to week 4, folks. Week 4 is kind of exciting in the semester. Once we're done reviewing for exam 1 on Thursday of this week, we'll be across the 25% mark for the entire semester. So that might feel like it's going pretty fast depending on your perspective. Feels like it's going fast on my end. Oh, didn't mean to do that. There we go. Let's bring that back. But welcome back. I have kind of a big wall of announcements to get through, but first, any questions that folks have right away? Okay, let's start from the bottom since that's the major thing to talk about so far. We're going to come into our very first exam, and this exam is going to be these 5 specific units. 2A, 2B, dealing with units. 2C is problem solving, and 3A, 3B that we're getting through. 3B is going to be the one that we'll probably finish today or potentially on Wednesday. And this is going to be the last one that's going to make up the entirety of exam 1. So Ed, I sent out the instructions for scheduling the exam first thing today. Sorry for the double email though. I made a mention that it's closed notes. That was for the other class I was trying to send out for, and I just accidentally misconveyed that information. Our exam is definitely open notes. It's going to be one 8.5 by 11-inch page of notes. It'll be anything you'd like on both sides of that, and it can be handwritten or typed out. And I made sure to include those instructions to all testing centers. So they'll be expecting you to come in with both a scientific calculator and your 1 page of notes. They're not going to collect these notes. So when you're done with the exam, just take it along with you. And it's a good idea to put it in a folder, maybe in a drawer somewhere, and have it ready to go when you're starting to plan for your page of notes for the final exam. Well, any questions at all, folks, about the exam at the moment? Okay, well, as far as scheduling the exam goes, it's a little bit finicky, I noticed, because our class is officially 70 minutes, yet I think ISU just expects everything to be in chunks of 15 minutes. So I wrote it the exam is going to be a 75-minute exam. You don't have to use that additional 5 minutes. But the trouble is when you go to schedule your exam, just about everyone in the class got a scheduling link that takes you to here. This one's for the Pocatello Testing Center, and there's a very similar one for the Idaho Falls Testing Center. And again, slightly different if you're, say, testing in Meridian. I sent the specific instructions for that center. First thing you'll have to do is click on the day. I actually have this exam open on several days. The trouble is a testing center like, say, the Pocatello Testing Center, which is very busy, it can literally fill up on Monday and there's no seats left. And also it has to work with your schedule. So I left the scheduling open between Monday through Thursday. So you can schedule on any one of those days that makes the most sense to you. The more ideal day is on Monday. That's the day we won't have class because someone could be scheduling the exam for right now, 6 o'clock a week from away today. If you schedule it on Wednesday or Thursday, you also have to think about it could conflict with the lecture as well. So be less hectic if you do it on Monday or even on Tuesday. But if there's any other kind of weird conflicts that come up in your schedule, we'll be fully open on these 4 days. So select the day that makes a sense. There's no same day scheduling, so I always try to be really on top of it and send out the link fully a week ahead. Then you have to select that specifically for the 75 minutes. And then from then, just pick a time slot where you want to begin your exam. Looks like this begins for this particular Pocatello Testing Center. The latest start time is 4:15 p.m., which again, that's kind of awkward for a night class like ours. And that's the reason it's open over a selection of days to best work with your schedule. Well, any questions at all, folks, just about the scheduling side or otherwise? Okay, well, aside from exam scheduling itself, the other thing that's going to happen on the exam is there's a formula sheet. But this sheet is going to be just part of the exam itself. It's going to be the very last page once they hand you the exam in the testing center. So again, all you need to bring is your scientific calculator, your page of notes. If you were to thumb to the very last page of the exam, after putting your name on it, that wouldn't be a bad strategy because then you'd be looking into the information that's provided. You might have noticed that we've cited these tables a lot, it turns out. And we'll cite them some more. I already have these tables pulled up and ready to go so we can use them in the notes we're about to solve. And so I thought for that reason, this was a good page of notes to have at the very end of the exam. You have a page of notes you'll bring, but I felt like just copying this kind of information here would be just a nice resource as well. So you'll be using this as needed. If you put it on your page of notes, then you have some redundancies there, so there's no harm done on that sense. So aside from the things that are provided, things to bring, as far as studying for the exam goes, we talked a good amount about that last time. Good ideas to get caught up on all the quizzes. Quiz 2 is going to be due Thursday, and I'll be working on getting this graded as soon as possible. Probably I'll be grading them, looks like I have been grading them pretty much the moment I get them. And once you send them in, I'll be sending in your feedback. I'll be posting quiz 3 shortly, probably before we come to Wednesday's class. And quiz 3, I'm going to be based on, I believe, a 3B question. So if you go through quiz 1s, 2, and 3, get those sent in, solved, look at any feedback I give you if you lost a point here or there, that'd be a good way to get prepared for what exam questions look like. And then going beyond, if you get caught up on the homework in my lab, you're doing great and getting prepared for the exam. And these are just additional problems you could take a look into. If you're fully caught up on everything, but you want to get to study a little bit further, then I provided 2 versions of the sample exam. Version 1 is the actual lecture notes. But what I've done with the lecture notes is I've taken out all the formulas. Some examples were really just kind of warm-up questions more than anything. I took all those questions out, and I left it on the questions that actually look like good exam questions that you should expect to see on exam 1. So that's why our very first unit starts on 2A, or excuse me, 2A unit starts on example 6, 7, 8, 9. Those all look like great examples that could be exam worthy. Unit 2B starts on example 3. These are problems that we've solved before. So that means there's no solutions at the end of this document, but you can go to the Canvas page, just go to Unit 2B, and the solutions are posted there. So that's what's going on with the first version of the sample exam. It's my way of saying these are the problems that we did in class that you also did in the homework that could make it as a great exam question. And in version 2, its whole purpose is to give you actual new, fresh problems. So if these feel too boring, if you feel like you can look at the problem and you know how it goes, but you want just a different scenario, version 2 is cheating that. So these are all brand new problems. We haven't solved any of these before. Going through these on a section by section basis will be great practice. And notice it's 27 questions, but that's just to give you an idea of what is all the potential questions from Unit 2A all the way to Unit 3B. I'm not going to ask 27 questions on the real exam 1. That'd be a lot of work for me to grade. That'd be a lot of work for the testing center to print out a packet of questions that thick. I do put in a lot of space for questions. So what I'm doing is I'm just taking a representative sample of questions on a section by section basis. And I think this exam ended up with about 11 or 12 questions after I wrote it. I forget the exact number. I don't think it's over 12, about 11 questions. At the very end of this document are the answers, and I make mistakes too. Typos are just legitimate mathematical mistakes. So if you see anything correct here, just let me know, and I'll be happy to double check it and get it revised as soon as possible. So that's the full rundown of all the exam materials. And essentially, what we mentioned before, when we go across the weeks in Canvas, say all the way down to week number 10, we'll just do it all over again. Before you show up on week number 9, there'll be all the information in the exact same order. The formula sheet, 2 versions of the sample exams with the same theme on each version. And so we'll just get in a kind of a habit of going through this on a week-by-week basis. Trinity says, I'm not sure if you already answered this, but will we get the conversions of measures of units on the test, or do we need to write them down on our own paper to bring with us? So it's pretty much, as far as the conversions go, I have the formula sheet that's attached here. So this information right here will be provided, and it'll be a pretty good answer key for a lot of different conversions, say USCS to metric and so on. And if I give you anything that's kind of random, we saw some random units ourselves, like say out here, if I give you anything that involves a nautical mile or anything that involves a troy ounce or a dram equals 3 scruples, if I give you anything along those lines, I'm going to write that into the problem itself. So that way you won't have to feel like you're writing down every single possible thing that could potentially come up that you saw in the book. More, I'd say the things to bring the notes are things along the lines of formulas, like say the percent formula for looking at absolute change, percent change, those kind of ideas. If you put an example that you'd like to refer back to, that's open as well in this exam. Since I won't be checking your notes, it'll be fully anything you think might help out. But does that help with that question there about the units? Yeah, absolutely. And now that you mentioned that, a great idea to keep in mind when you're studying for this exam, even when you're doing the homework or the quizzes, is refer back to this formula sheet. Use this to study for the sample exams and such. Because if you're pretty familiar with where everything is, what's provided on this exam, then once you actually get the real exam with this on the very back end, you'll know exactly where all the information is going to be provided. And at the same time, you'll have a great idea in your mind of what do I need to put on my formula sheet that's not here. Again, that's kind of a interesting exam going into an exam one for the very first time for a course like this. But we'll get a great feel for what these exams look like after the first one. Exam two, I won't be doing anything too different. It'll be just different sections. Braxton says, so we could take a page of notes to the exam. Yeah, absolutely. And as far as studying the exam goes, I gave all that advice on Thursday's class, but maybe another piece of advice that I just didn't remember to say, which is really good advice, is start working on that one page of notes that you can bring to the testing center sooner than later. I'd say if you're putting this page of notes together and it's 1 hour that you're about to, say, get in your car to drive to the testing center, that's really stressful and your notes probably won't be as impactful and helpful as they could be. But if you start off, say, maybe on Friday, you got caught up on the quizzes, the homework, you're about to take a look into these exams problems, start building out your notes there. You might notice you did a question and there's something you really wanted on those notes that you had to look up. As you're studying, say, version two, that's a good thing to throw onto the notes as well. Get that settled early before even the day of the exam, and you'll be in great shape. Other questions so far? Okay, and we'll talk more about the exam because, like we mentioned, and we're going to stick to it, for every one of our exams, you might have noticed in the day-by-day schedule, we'll have a review day. So we'll be reviewing exam one content on Thursday of this week. We have to keep moving forward in the schedule, and I hope to get 3B either done today or pretty early when we come back on Wednesday. Then we'll move into 3C, but Thursday is all about just talking about the exam. I think I had another thing I was going to say, but I've forgotten. I'm sure it'll come back to me. Oh, one thing I did mention is our review on Thursday is meant to be kind of a student-directed review. So if you have questions that you'd like to take a look into, maybe it's a particularly nasty problem you might have saw in my lab or otherwise somewhere in the notes, don't hesitate to ask. I want to start with any questions you have first. And then if we run out of the student-directed questions, then we'll just go to some problems that I'll have prepared. Then I'll post the problems that we'll review, the extra problems down here on Canvas as well. Well, I think that just about covers it for the announcements. We're getting into an exam, so it makes sense we've gone about 14 minutes in. Other thing to mention is last week, I think this happened either Tuesday, maybe Monday, but I think I noticed personally on Tuesday, the 27th, if you opted out of the ISU Book Bundle program, then the MyLab system through Pearson has taken out access to both the eText and MyLab, which is always bad timing going into another exam. So that's a good idea to get that access renewed as soon as possible. It does cost $95 for the single term access. And watch out for anything that says multi-term access. That's meant for a book that goes from a class that lasts for several semesters, potentially. As far as the due dates go, if you are waiting for payday, anything like that, you're not going to be fully penalized on getting behind on any of those sections. As far as the due dates go, they're really just for the sake of pacing. And so you can always, at any point, go back to any one of these sections that are past due to continue working for full credit. I think I'm really out of enhancements at this point. Any questions or comments at all, folks, before we get started? Okay, again, probably get the exam scheduled as soon as possible, maybe after class today or first thing tomorrow morning. If you run into any issues, let me know. If I made any mistake, if I sent you to the Idaho Falls Testing Center, but you really actually tested Pocatello, let me know and I'll get that corrected as soon as possible. But here's where we left off in 3B last Thursday. We were discussing scientific notation, and we're going to see how this connects with the material in this section. We'll be using this as we go off into the next section, 3C as well. And just for a quick refresher on this, scientific notation is said to be, or a number is said to be in the format of scientific notation if it's some number multiplied by 10 to some power, any power whatsoever, even power 0. Typically, we're looking at a high order magnitude like this for a large number. For very small numbers, we're looking at a negative value to say a small order of magnitude. The number being expressed between 1 and 10 just means we have to shift the decimal point until we land at some integer value, not 0, and we can't go beyond, say, 9.999 and so on. So for the last problem, essentially all we did was we took the number 0.00416, we shifted it to the right 3 decimal places. That got us the number between 1 and 10. But when we shifted it to the right 3 places, we made it bigger by a factor of 10 to the power 3. So to counteract that, we changed directions and multiplied by 10 to the power negative 3 so we could get back to the original number. So that was our refresher. Now we're going to start all over again with part C and then move into some computations and then some scenarios with context after that to finish the unit. Any questions whatsoever on the refresher page so far? Okay, let's try it out with the new problem then. We have 518.29. If we want to put this in scientific notation, then the decimal point we're tracking is right here between 8 and 2. It's going to move left 2 different places. So that's hard to leave the red dot where it is. There it goes. So the number we'll get is 5 point. Let me switch colors here. So 2 places to the left, giving us 5.1829. Then we multiply by 10 to some specific power. But think about what we started with. We started with a large number. We shrinked it down from 500 roughly to 5 roughly. That means the power we have to put here is big to counteract it. But if it was 2 places to the left, that means the power goes up by 2, and we put in 10 power 2. And that's what we're highlighting here. If we move something left, the power is going to be positive to counteract that decimal shift. If we move something to the right, we made something bigger. And so we go the opposite direction and put in a negative power. And that's, again, kind of strange little mental white noise we have to navigate when the directions seem opposite. But it's just undoing what we did with the decimal shift, putting in the positive power there. Well, any questions at all, folks? Getting through that last part we ended on? Okay, the next page isn't anything too different. Really, it's just kind of a refresher on scientific notation, and then a refresher on dealing with powers of 10 and some operations with scientific notation. Again, this starts to answer why did we focus on exponential notation so much, and I believe that was Unit 2B. It's because these things just sort of come up in the computations we'll do later on in this section with the problems with context. It says do the following operations, express the answers in scientific notation, And let's just laser focus on this one, hide the rest for the moment. The idea with this one is you can really just start by organizing your numbers. Multiplication is commutative, and we mean that in the sense that you could rearrange this into any format that might be helpful. And one nice format is organize just the ordinary numbers together. So now it's a 4 times 2. Then shift things around, take the powers of 10 and bring them next to each other. So times 10 power 5 times 10 power -8. Then, because exponential notation comes up so often, think, what is the exponent law I need? A power of n times a power of m. This might be stuff, for example, that you might want to include on your exam 1 formula sheet. We have these kind of in the same color throughout the notes whenever it came up. And the exponential law is that these add up to an n plus m. So we'll refresh these as we go. That means this problem is going to end with an 8 times, I'll write it out this way just to match the notation we typically see for scientific notation. Here the powers add together, so this becomes 10 to the power 5 minus 8 for a -3. And that puts us back into scientific notation on that last step. We have to be careful though. Some of these, when we multiply the numbers, you have to do an extra step if that number is not between 1 and 10. Well, any questions at all, folks, getting through this one? Okay, let's try it out again. Part B, it's the same kind of idea, just different numbers now. Here's where we need to be just a little bit more careful. We have 7 by 3, so when we multiply those two together, we're resulting in a 21. But let me reorganize it this way, just to visualize it better. Here's a step in the middle that you definitely don't have to show, but for organization's sake, it's pretty good for the notes, I'd say. Take 7 times 3 times 10 power 8 times 10 to the power 7. Our last number was really quite small, but this time when we add up the exponents, we're getting a gigantic number, 10 to the power 15. It becomes 21 times 10 to the power 15 altogether, once we add the exponents on those power 10. And this is one of those problems where it could be kind of vague or not completely descriptive when we put in this number, and MyLab doesn't accept it. And you want to see what the problem is with this number as it stands.
It's not between 1 and 10.
Yeah, exactly. So we didn't do anything wrong with the arithmetic, but now we have to be really verbatim with the instructions and put this number, as you said, between 1 and 10. So here's the step in the middle out of nowhere. 21 we could rewrite in scientific notation itself as 2.1 times. Well, thinking about this, we move the decimal place 1 to the left. So the power of 10 should be 1. Or in other words, we made it small. So we multiply it by a large value, 10 altogether. And that itself is multiplied by 10 power 15. So we have to combine all of our powers of 10 to result in 2.1 times 10 to the power 16. Well, 16. Let me try again. This is one of those problems where if it was something that came up on an exam and you had to put it in scientific notation, but you landed here, out of a 5-point problem, I might take off a half a point because that's pretty close. But MyLab doesn't care. They're going to force us to do this, so it's all or nothing for MyLab. Watch out for those small little things that could crop up in the homework. Well, any questions at all, folks? Getting down to that answer here. Okay, let's do one last refresher problem, and then we'll move into the larger questions with context. So same operation, but this time we're dividing. You know, when you're dividing things, the organization of this can look a little bit strange. But here's some optional steps just in the middle to think about this one. You could just take 8 divided by 20, 10 power 15 divided by 10 power 9, get the values, make sure it's in scientific notation, and then you're done. But for a real process, here's a good step-by-step way to go. Let's just re-express the division and call this 8 times 10 power 15, 20 divided by 10 to the power of 9. So these would be considered optional steps, and you can imagine if you had to do this on an exam, you might be worried, am I ever showing enough steps? The overall guidance is always going to be along the lines of, if you could do something in your head, if you knew all you had to do was, say, grab a calculator, take 8 divided by 20, and then take power 15, subtract power 9, and just put it together. If you didn't show these steps in the middle, I would still say that that's no big deal. We have to show steps, but anything you can do on your head on your own, you don't have to show on paper. But the other side to that is I grade on partial credit, so I'll give you plenty of time to show step by step. And if the more detail you give me, the more basis I have for partial credit. If all you gave me is a number with no work whatsoever, that's perfect. You get 5 points out of 5. But if there's a mistake and I'm not sure how you got your number, we could lose everything on this one. Even if there's a strong chance you knew exactly how this goes, showing some steps is just kind of like insurance, a paper trail on how you put the thoughts together. So I'm putting in a lot of steps on this one just to break down what the shortcut looks like. Once we get here, we can use another property of fractions. You can break this up into one fraction times another fraction in any convenient way you'd like. And for me, a convenient way, once I get the numbers right, would be take 8 divided by 20 and then go 10 power 15 divide by 10 power 9. Because now I'm breaking down the integer part while using scientific notation and 10 to some power part in scientific notation, much like on all the rest of the problems. It's a lot of steps, right? But the logic here is that's essentially what I mentioned the shortcut is. Take 8 divided by 20, 10 power 15 divided by 10 power 9. And now we just see how that comes together. Any questions at all, folks? Just getting to this step? Okay, it's kind of weird when you think about it, because when we are dealing with fractions, we're almost always going this way. We're always told to multiply across the tops, multiply across the bottoms to get that. But sometimes it's a good idea to just reverse the entire process, whether you showed this step or not. Logically, what we're doing in the calculator is undoing the entire process of multiplying two fractions, going the opposite way. And here's what we'll get. So now we're finally back with the calculator. 8 divided by 20 gives us 0.4. Then multiply that by new exponent law. We mentioned here in this configuration, the power subtract, but let's write this on paper. A power of m divided by a power of n is a power m minus n. And there's a certain logic to that, right? If you multiply, things should add. If you do the opposite operation, divide, things should subtract. And so that's what we're seeing here. This then becomes 10 to the power of 6. But just like the last part to be, if you're noticing, aha, this is not done, good on you. We have to keep going on this one, get it back into scientific notation. So this is one of those problems that just seems to not want to end right away. Next step is to put 0.4 in scientific notation. It turns out it's the same as 4 times 10 to the power 1. So again, the logic is, hang on, I messed that up. Anyone see what the right power should be for this?
-1.
-1.
Good call, thanks, folks. It's always good to, once you have something you're about to put down on paper, just think about it for a moment. There'll be plenty of thinking time because it's easy to make the simplest mistake and then suddenly being off by a power of 10 out of nowhere. Yeah, if we take something small, make it big, we have to make the power go up by 1. Or another way of thinking about it, move the decimal right one spot. Oh, and I messed that up again. The power needs to go down by -1. Thanks for mentioning that, folks. That one, for some reason, was a tricky one for me. Then take this, multiply it by 10 power 6. And we just about have this one. This becomes 4 times 10 to the power of 5 altogether. And by the way, you don't have to put the time symbol if it feels like it's taking a while. If you leave your answers with a dot symbol like there for multiplication, I'll be completely fine with that. Think of this as more just a stylistic choice of expressing the scientific notation. But that's our warm-up so far for this section, the rundown of scientific notation and operations with them. We'll come up here and there in the notes for this section and in the following sections throughout the course, particularly 3C, this work will come up again. Any last questions or thoughts on scientific notation so far? Okay, well, let's get into next the problems that actually have context. So here's how they're going to start. Let's just kind of take a tour of the notes to see what we're getting into. The next problem, part C and A and B, is nothing too major so far. We're just practicing more scientific notation, thinking about units. And so this table makes a nice comeback as usual. This seems to be our most cited notes, and our most cited two tables is this one and the conversion table. Then we'll ask and answer some larger questions. The unit is putting numbers into perspective, so it's easy to cite a number with units and have really no feel for what that looks like. And that's what we're going to be doing in problem 4, asking and answering the question, could the average person lift $200 in nickels? This is a random question. If you work for a bank, you probably know the answer to this potentially. Another one that's even more random, it feels like. This one we might want to Google something or just ask people in class what seems reasonable. The number of breaths a person takes in a year. I won't ask a question like that in an exam setting without putting down an assumption on paper because it feels too open-ended in that sense. And even in my lab, they just give you a number. They'll say, assume the number is this. But we'll make this one a little bit more exciting and open-ended by either Googling or just asking the class and seeing what we feel is all reasonable. Then we'll do an energy comparison in joules of burning 1 kilogram of coal versus the amount of energy released in fusing 1 kilogram of hydrogen. And that's going to be our pretty much rundown of putting numbers in perspective for this section. And the next section, we won't be doing anything too different from this kind of work. Scientific notation comes up, but then percentages come up again as well. So even though the next section is not on exam 1, we'll review percents, which is exam 1 content. So that'll be helpful at least. But let's get started with 3A. It says rewrite the following statements that we see using a number in scientific notation. So using that same rule set that we've been practicing in our warm-up problems, here's the first problem. The number of different 8-character passwords with 26 letters and 10 numerals, so no special keys, which is almost like a requirement these days for a password. If we don't even use the special keys, there's approximately 2.8 trillion passwords, which sounds impressive, but computational power is so high these days that it can potentially crack a password with 2.8 trillion possibilities in a small amount of time comparatively. But all we're doing here is putting this into scientific notation. And because the word trillion came up, not a bad idea to think of the prefix tera. Tera, or T for trillion, could be anything, say a terabyte, a terawatt, a terameter, in fact. Involves a power 10, 10 to the power 12 gives us trillions. So one way to think about this problem is you could write out 2.8 trillion as 2.8 equals 2 trillion, 800 million. Those are the thousands. Let me double check my work here. So that's the trillion, billions, millions, thousands. And then hundreds, tens, and ones. We could start off by going in that route. Or another great way to think about it is the number here is kind of giving us just about everything we need. We could just say 2.8. Thinking in terms of this table, which is provided on the real exam, multiply it by 10 to the power 12 because it's trillion passwords. And we're done really immediately right at that step. It's a number in scientific notation. But if we went first principles, wrote out 2.8 trillion in the standard form, notice what we would have had to do. We have to move back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places, making the number of 2.8 times 10 power 12. So either way we kind of visualize this problem, it's the same exact process like the first examples on these notes. It just feels different now that we have units, prefixes, the table here suddenly makes a comeback out of nowhere. But any questions at all, folks, with 3 part A? I knocked over my water. The lid was on, so no worries. Okay, let's try out the next one. This one's a little bit more scary. There's different kinds of hepatitis. I believe hepatitis C is the one where this could kill you. I think this attacks your liver over time. It's a very scary virus. But what we're here today to discuss is its diameter. If you were to put this under a microscope, this one comes out at 50 nanometers. So we're just expressing this in scientific notation, but again, this is a pretty nice warm-up problem. We could take 50 nanometers and rewrite this as, let's see our table once again. We're on the other end where things are small. And when we say nano, we can use N to describe it. So 50 nanometers could be written as 50, NM, M to refer to meters in the problem. That didn't really do it. I just paraphrased what we wrote here, but it gets us started because then the next part of the table tells us 50 nanometers is 50 times 10 to the power 9 for billions in meters. So this becomes 50 times 10 to the power 9 meters. And we're not quite in scientific notation. We have that same obstacle we've been looking into in the notes. But all we have to do is do a decimal shift on this number, write it as 5.0, let me see if I can get this part right, times 10 to the power, we made it small, so this should be 10 to the power 1 to bring it back to a larger number. Take this down, multiply it by 10 power 9. I wanted a different color on that. Let me backtrack. And we're pretty much done. We just have to combine the power of 10. This comes out as 5 or 5.0 if you prefer, times 10 to the power 10. I forgot my units along the way, so let me copy them in. Meters here and meters here. So the diameter of a hepatitis C virus, we can now say is 5 times 10 to the power 10 meters. Well, any questions at all, folks, with either one of those?
Yes, could you not just keep it in nanometers? Why did we have to change it to meters?
Oh, only because of the instructions of writing it out in scientific notation. I wanted the specific power of 10 on it. So in the homework, that's what they're going for as well. But honestly, 50 nanometers is a perfectly fine number. It's really just kind of connecting the dots with the skill of writing it as the specific power of 10 in scientific notation. Does that make sense with that question there?
I guess I was just thinking you could write it in scientific form using nanometers, which was like the 10 to the negative 9. That's where I think I got confused.
Confused too now that you mention it. Thanks for mentioning that. It should have been -9 that I put right here. I'm not sure why I put in a +9 whatsoever. Let me fix this right here. I think a red is probably a good color for this. It should have been just exactly as you said, 10 power -9. And you know, another good piece of advice on a real exam is there's extra time to look over your questions and see if your answers, like the one I put here, passes a smell test. I'm saying that the hepatitis C virus is, well, very, very big. This is a lot of distance. This is 10 power 9 is billions, so 10 billion, the magnitude. There's no way that's true, right? So there's a correction there to make. Then when we do the addition of the exponents, this would become 10 to the power of -8 meters. So your question was also why just leave it in that form, but I think it was also about that mistake is there as well. Does that make more sense putting it down to that correction?
Yes, that's what confused me was taking it to the positive from the negative. I
Yeah,
didn't
exactly.
did that.
Oh, that's a mistake up there too. Let me fix that here. It's one of those issues where it looks like I probably had a weird like micro sleep. I miscopied from here to here at the very start. Then I turned off my brain thinking about the context and kept the error all the way down. And if this was a real exam question, I would grade on partial credit right at that step. And if everything you do is correct right thereafter, there's no double jeopardy. But this was a 5 point problem. I think that's a pretty serious mistake. I'd probably take off 2 if that was my own exam that I had to grade right there. Thanks for again for hitting the brakes on that one. Does that make more sense to everyone as well? Yeah, thanks for mentioning that as well, Amy. So let's recap. When we have numbers with context, at least, that's meant to be a big help for this kind of problem. Hepatitis C virus is supposed to be small, so we're expecting a very small order of magnitude, not something gigantic in terms of meters that could potentially travel across the United States. Well, that runs us through the warm-up questions. We have some larger questions there, so I'll try to watch for those kinds of mistakes, but hey, at least we got to have a discussion on partial credit grading and stuff like that. So beyond this question here, here's the other kind of questions you'll see in the homework as well. I try to keep this unit.
Sorry to interrupt you. I just had one more question about that problem. I was wondering if you could leave it without doing the last step, if you could leave it at -9.
I would probably be not too worried about that, except for scientific notation, you would have to combine the two different powers of 10. So I'd say on exam question, you might lose maybe a half a point or a single point. I'd have to decide between the two. But yeah, for scientific notation, it has to be just overall one single power of 10 in the problem. Does that make sense with that question there?
Yeah, thank you.
Yeah, you bet. Definitely not the same kind of issue of like forgetting the negative power and then not realizing at the end with the context of hepatitis C virus that the power is off. But yeah, small things like that, if you left it like this on a real exam setting, it wouldn't be worth too much as far as being docked on partial credit. But for following the instructions to the letter on scientific notation, really we had two corrections. We had to fix the 50 to bring it between both 1 and 10, and then finally combine the two base 10s as well. Thanks for asking about that one as well. Any last final questions on this example 3? Okay, let's change gears to more kind of interesting questions. Exponential notation comes up on even this kind of question as well. Let's put this one on a new page to see how it goes. And then exponential notation will come up in a big way on exercise 5 down below. Or example 5. I usually print example 4 rather than 4, but let's let that slide this time. Kind of a weird distraction there. So this one is kind of interesting and strange in a certain sense. When I see a question like this, my gut instinct on the answer without doing any computation is I have no idea. I can't visualize $200 in nickels. That's impossible. So we have to do some sort of unit conversion to get to this problem and see where this is going to end. We know a single nickel is exactly 5 grams. And if you have a really good head for grams and you gave an answer in grams, I think that'd be all right. But my lab is kind of specific. They usually choose a unit for us, and the most sensible unit for a problem like this might be in pounds. We're just familiar with that kind of unit. So let's say we're going to convert $200 in nickels to find out how much this weighs in pounds. So that will be our overall answer we're going to go for. Let's start off just with the unit analysis of saying, well, as far as money goes, $1 is equal to 20 nickels. because nickels is 5 cents and 5 times 20 gives us back to 100 cents, making the $1. And that's going to start getting us into nickels to kick this off. So we can begin with the quantity given, $200 in nickels. I think though there's a problem in my lab that involves quarters, so something along the same line. We can now multiply this by 20 nickels per the $1. Or let's make that unit look just a little bit more compatible on that line. We could write it this way just to make sure the cancellation makes a little bit more sense, expressing it in the same way. And we're also given a hint on this one. Let's say if this was a real exam question, I would have to give you this kind of information. I'm not expecting you to try to anticipate random things like knowing the weight of a nickel in grams, or the amount of mass is the better way to say it, of a nickel in grams. So this is saying 1 nickel equals 5 grams. And that would be our next conversion factor to throw in. We can multiply this by, the logic here is we want to cancel nickels. We should put the 1 nickel in the denominator. Then the weight, well, not exactly weight, the amount of mass, 5 grams, in the numerator. And that gets us started. We now have an answer in grams. But let's go for the gold standard, something that will more likely than not be going to be asked to do in the homework. Let's put this into pounds. So we need a bigger conversion factor. So an exam question like this one will provide the overall information like this one, but there could be some information that we have to investigate through, say, a table like this one. Well, we have kilo per thousands, and we might be able to relate that to something. And up here, this is the other table provided on the exam. We're told, here's what we want. 1 pound is 0.4536 kilograms. Already highlighted, that's kind of nice in a way. So let's bring that in. 1 pound, 0.4536 kilograms. Okay, that gets us started, except we have another problem. There's grams in here to work with. So if we want to work with that, we can come down and deal with the kilogram. We could say 1 kilogram is 10 to the power 3 in grams through this part right here in the table. So let's write that in. 1 kilogram equals 10 to the power 3 grams. Let's double check that. So pretty much it's just this side of the table, using the right power and double checking that now at this point, and just putting a G for grams on both sides. So I think we have all the conversion factors we need to get through this. And I'm not sure if I thought of that right. Let me put in just a little bit more space. And I think we can start multiplying through in this problem. We want to cancel grams, so we can take the grams right here, put 10 to the power 3 grams is 1 kilogram. So now we're in the unit of kilograms. And last conversion factor will take this to pounds. Times 1 pound to the 0.4536 kilograms. And if everything is working the way we want it to work with the unit analysis, we should be able to cancel and get an answer in terms of just weight in pounds. So cancel here to here, dollars are gone, nickels are gone, grams cancel, kilograms cancel, and now we have an answer in just poundage. We just have to put this all in the calculator at this step. Any questions or comments to this stage, however? Okay. Truly, the tie-in with scientific notation wasn't really big on this problem, but it'll be bigger on the next problem that we're getting into. But you know, it's there, the kilogram to 10 power 3 grams. But one thing I want to mention, because we're all thinking about exams, is the following thought. When I grade exams, I like to grade mostly on the logic of how you put all things together, And I understand when you're taking an exam and just typing things on a calculator, pretend this is your calculator, it's easy to make a mistake, even if you had things completely perfect in your mind. But you know, if it's perfect on paper, exactly like this, and this is your real exam, even if the number is completely off, I'm just going to assume you made a mistake in the calculator. I'm not too worried about that. But this is the logic I'm really trying to grade on. And so the comment is, if this is correct on paper, you will get full credit, even if there is a calculator mistake. A calculator mistake is still serious because if I make a calculator mistake, my number just looks weird. Weird in the sense like I forgot that that had been a negative exponent, for example. My number came out weird and I don't trust it. I might think that I just did the problem wrong, maybe erase the work, try to backtrack, and never actually get to the end on this one. So the calculator is still important, but if there's a simple calculator mistake, if I see all this stuff on paper correct, you would still get 5 points out of 5 on a 5-point problem. And the other idea is units are pretty much the only thing that told me this is 20 over 1, 5 over 1, but 1 over 10 and 1 over 0.54536. I'm not going to grade on units, but I encourage you to write them in just as a way to make sure the numbers are coming in together the way we expect them to. And I feel like grading on units, I'm not going to be really heavy on that only because I've mentioned this before. MyLab prints all the units, so it makes that not really a great objective to test on if MyLab just puts that into the homework assignment on just about every problem. But now with this all on paper, let me know if you're getting something different in the calculator and we'll work through it together. Here's how we would probably punch this in. Some calculators just let you type in one entire line, so you could go 200 times, 20 times, 5 times. Here it'd be 1 divided by 10. Times 1 divided by 0.4536. And this is the value I would get, except it looks like I made a mistake in the calculator. That's 1 over 10 power 3, so don't forget the exponent. 10 to the power 3 definitely changed the number to, I'll also say what to round to, but let's go for the nearest tenth of a pound. Forgot on this one. 44.1 pounds. How's that look to folks? Any questions on just getting it into the calculator or otherwise? Okay, well, that's a healthy chunk of weight. So at this point, this is the subjective part of the problem. If you have 44.1 pounds, you still have to answer the question, but I'm going to just leave that be your judgment call on this. I would say, yeah, most people on average could probably lift with your legs. You could potentially injure yourself lifting nearly 50 pounds from the ground, for example. But I would probably personally say yes to this. Yes, the average person can lift the weight of $200 in nickels. It's going to be heavy. If you have, say, a front wheel drive vehicle, you could put this in the back to get some traction on the back tires potentially. But any last questions on the top to bottom analysis on this one? Okay, again, that's pretty much what this section is all about, putting numbers into perspective, taking something that seems silly, vague, and hard to visualize, very, very hard to visualize, using all of the tricks we've been developing so far, unit analysis, and a little bit of scientific notation here, we can get a good feel for what we're discussing, 44.1 pounds. The next question is going to use scientific notation in even a bigger way. So Here's the one that's a very open-ended kind of question. I feel like it would make kind of a bad quiz problem and even a worse exam problem. There are questions like this in the MyLab homework, but they give you assumptions to work on. So again, we're going to come up with our own assumption to get through this one. And the big idea here is we're trying to come up with an order of magnitude estimate for this kind of quantity. So we're not necessarily trying to expect a really precise answer whatsoever. We're trying to get an answer between a range of the right power of 10, so just a very rough estimate. So just the quick definition says an order of magnitude estimate specifies a broad range of values, usually with 1 or 2 powers of 10, such as in the tens of thousands or in the millions. We're going to give just 1 power of 10. So it'll either be in the millions, billions, maybe 100 millions, and so on. And we'll emphasize it with a number in power as a power of 10, so otherwise using scientific notation. So this is not meant to be an accurate answer, but just a really rough order of magnitude estimate of the number of breaths a person takes in 1 year. And there's a lot going into that, right? You might wonder, well, very young people, say babies, probably have a faster heartbeat. Do they breathe faster? What about super athletes that are training all day and just huffing and puffing away on a treadmill? But we're not looking for the extremes. We're trying to average this all down into just the average person over the course of, say, maybe 1 minute to start. How many breaths would you all say that a person takes? Number of breaths. Let me spell that right. In 1 minute, that's a good basis for our assumption to make, is approximately and I'm not sure. Anyone have a good guess or value for this? I'd say 30 is possibly on the high end, but as far as an order of magnitude estimate goes, it's not that far off, really, if we went with the number 30. Any other volunteers for a value? Some for, say, 15, 20. I think those are pretty realistic values that could come up. And there's an easy test, right? You could just take out a clock, watch the minute go by, and count the number of breaths you take, except that's kind of a mind game. If I'm thinking about how many breaths I'm taking, I might change the number of breaths per minute I'm actually taking if I'm thinking about it. So it's a tricky number. And if we did something slightly different, if we want to make a gross approximation order of magnitude estimate, any one of these values, 30, 15, and 20, is going to give us pretty close to the answer. We have 3 candidate answers. Thanks for those folks. Let's average them. Let's take 30 plus 15 plus 20, divide by 3. I'll round this down to a 21. That might be slightly on the high end, but it's okay for an order of magnitude estimate kind of problem. We say what our assumptions are and give the value, we're probably going to be within the right, close to a power of 10 of a true answer. And by the way, if you Googled it, I think Google gives a range of, say, 12 to 20. But let's use the values from the class given. I'll go with rounding down 21 breaths per minute. So we'll say here, we'll assume, or assuming, the number of breaths in 1 minute is approximately, I think I said 21, I already forgot. Yeah, let's go with 21. So that's our baseline piece of information to get us started. And if this was an exam question, I would give you a number. It's way too wide open otherwise. It's a hard question to start, in my opinion. But again, thanks for the responses on that. Pretty wide open kind of question there. Now we want to know the number of breaths a person takes in a year based upon this approximation. So let's get started. First, we can say if we take 21 breaths in 1 minute, we've used up the entire assumption here already. Next thing we have to do is get it down into a year. But we've done these kind of unit conversions before. I think we looked into the number of heartbeats or something along those lines, or the number of seconds that goes by in a 16-week semester. The idea is we want to get our time value to get a little bit larger. So we go from minutes to hours. And we know that there is 60 minutes to the 1 hour, but minutes are in the denominator. We should put 60 minutes up into the numerator so we can get the cancellation like in the last problem. So we have 60 minutes to the 1 hour. And then we just keep on going along those lines like we did before. To cancel hours, we can put in 24 hours to the 1 day. Then we're going to take it to years. Here's where it gets kind of tricky as well. The year is not exactly 365 days, but that's okay. That's a decent approximation to make. If we're just going to a broad range of going for a broad range of values in an order of magnitude estimate. Let's just say 1 year is 365 days. And now I think we have our units all lined up. The unit analysis has to take us to breaths in a single year. We have breaths per year. If we look at the right end and the leftmost end and the rightmost end, we are just double checking now, are we doing the right multiplications? But minutes to minutes will cancel, hours to hours will cancel, and so will the unit to day with days. So our number, conveniently with ones all in the denominator, passes the unit analysis test. So we're just about there. Last thing we'll do is convert it into scientific notation. But any questions first before we throw all this into the calculator? Okay, so going with the average response in the class, here is our answer. Take 21 times 60 times 24 times 365, and we're coming up with, looks like 11,037,600. I think I missaid that, 37,600. Breaths per year. So we're pretty much done with the problem. We'll just convert this one into scientific notation. And we have our so-called order of magnitude estimate. So we're going to move the decimal point all the way to here, go 1.1. This didn't say anything along the lines for rounding, so I'll keep all the values all the way to the 6. 0.376, then stop right there since we don't need to write down further zeros. Multiply that by 10 to the right power. This is our scientific notation side. Anyone see what the right power should be for this one?
Seven.
Yeah, good call. We moved this from here, the far right spot, 7 places to the right, making it small. So we need to expand out that number 1.1 and some change with the power 7. So now we brought it into scientific notation. Our number over here is between 0 and 1. And finally, that's also our order of magnitude estimate. We can say that the number of breaths in 1 year for the average person is on the order of magnitude 10 power 7. The actual answer we give MyLab statistics would be this number right here, But if we really only cared about the order of magnitude, it would be this number. We know we're not perfect with 1.1, not even close. There's a lot of assumptions we might have to make to get this just dead on. But the true number is probably bigger than 10 power 6 and probably smaller than 10 power 8, or just somewhere in those range. That's why we say an order of magnitude estimate sometimes has a range of values. And this is just our best guess of that order of magnitude. It's in the order of magnitude 10 power 7, in the tens of millions, in other words. And what if we change our values? What if we went high, like say 40 breaths per minute? You know what? That doesn't change the order of magnitude. It's still 10 power 7. So even if we had a really, really blunt assumption here, 40 breaths per minute, that sounds like hyperventilation. Or if we were really low, 5 breaths per minute, well, on that one, that would drop that order of magnitude to 10 power 6, but that's not too far off. We can give a really great estimate just on pretty fast assumptions like these and track in the units, giving that value. Well, there'll be other interesting order of magnitude kind of estimates that you'll see in the notes. A lot of things having to do with the scale of the universe, things along those lines. But any questions at all, folks, with problem number 5? Okay, again, these are the kind of questions that make me slightly uncomfortable. Just for the sake of reassurance on an exam, if this was a real exam question, maybe say a final exam question, I will give the assumption there. So it's a more direct kind of question. You won't be expected to just say, like, pull out a watch and time the number of breaths you take in an exam setting just to answer a question. I think that's going a little beyond what is required for a good exam problem. With what we have coming up next, this will be our final problem for the notes. It goes along the context of putting numbers in perspective by just looking into, this time, energy released. The energy released from burning 1 kilogram of coal is 3 times 10 to the power of 7 joules. That's kind of a weird unit. This is a unit of energy. And a great way to think about it is if you lift a medium-sized apple at 100 grams of mass, 1 meter, so pretty much above your head, for example, that's about roughly 1 joule of energy. Or a more precise value is if you take 1 gram of water and increase its temperature by 1 degree Celsius, that expended 4.18 joules of energy altogether. So we have a good idea what the unit is, even though it's a pretty precise scientific unit. Think of it as just a amount of changing temperature or the work you do lifting something against gravity. And we say 1 kilogram of coal is approximately 3 times 10 power 7 joules. So on the order of magnitude 10 power 7, but 1 kilogram of hydrogen is on the order of magnitude of 10 to the power 14 joules. It's hard to get a really good feel for the impact of that number until we do the comparison. How many times big is this really compared to 10 power 7? But in terms of order of magnitude, we'll give a more precise value. But in order of magnitude, it's really 10 power 7 divided into 10 power 14. So we could say that energy released for burning hydrogen is on the order of magnitude 10 power 7 times as much of that of burning the same amount of mass of coal. But we'll give the more precise value once we have more time with this on Wednesday's class. But any last questions at all, folks, thinking about any of these kind of ideas? Okay, thanks for your hard work and participation, and particularly spotting the weird stuff like that. I appreciate the call outs on those things. We'll be back to the notes, finishing this one off on Wednesday. Then we'll move into 3C, talking a little bit more about errors, percent errors, and those kinds of things before wrapping up for our review on Thursday. But have a great night, folks. If you have any questions, I'll be happy to help out. Otherwise, I'll see you Wednesday.